In this problem, we're looking at just a simple Diels-Alder reaction here, and what we want to do is figure out the delta H of the reaction two different ways, using bond dissociation energies and then using the Benson's group increment values. So let's start with the bond dissociation energies. And I do want to mention here that you can get slightly different numbers depending on how accurate you try to be. And I'm going to keep this pretty simple, but really there's a lot of changes going on even in the CH bonds, where we have CHs on sp2 hybridized carbons versus in the product CHs on sp3 hybridized carbons. We have allylic carbons we could account for. So there are some things we're not going to really get in the weeds with. We're just going to look fundamentally at the major changes going from pi bonds to sigma bonds. So let's start. If we look in our reactants, right, we have 3 carbon-carbon pi bonds. So we have this pi bond, this pi bond, and this pi bond. And then we have a carbon-carbon sigma bond. All right, so that's what we're going to look for. And we could just consider the pi portion breaking and not account for the sigma bonds. But what I'm going to do is really just use numbers that would imply all 3 pi bonds are completely breaking, as well as the sigma bond. So let's look at a table of bond dissociation energies. And I'm just going to use the one from the textbook. So if we want to find a carbon-carbon pi bond and the energy cost to break it, we'll just use this, 174.1 kcals. There's 3 of those. Right, and then we'll also account for the sigma bond, and the reason I'm including it is that we're just going to think about this sigma bond completely breaking and being replaced by the complete formation of a pi bond. For the carbon-carbon sigma bond, I'm going to use this value, 90.1. Now again, this isn't perfect because this is a methyl-methyl bond, whereas the bond strength of this is going to be a little bit different because it's connected between 2 sp2 hybridized carbons, but this is close enough to get us an estimation. Okay, so in our reactants, let's add these numbers up. End up with 612.4. All right, so now let's do the same thing with the product. And we're just going to use the same values to keep it simple. We have 1 pi bond, so that's going to be 174.1. And then in the product of 1, 2, 3, 4, 5 carbon-carbon sigma bonds. And we're just going to use the 90.1 for all of those. All right, so let's add that up for the products. Get 624.6 kcals per mole. So this is already telling us that the bonds in the product are stronger than the bonds in the reactants, so it should be a favorable reaction with a negative delta H. but let's go ahead and do the calculation. So the delta H of the reaction is the sum of the bond association energies of the reactants minus the sum of the bond association energies of the products. And we've already calculated those sums, so we're just going to do 612.4 minus 624.6. Do the math, and we get negative 12.2. And that negative value tells us it's an exothermic reaction. Again, you might get slightly different values here depending on the table that you use, also how carefully you consider each of the bonds that you're breaking. Now we're going to do the calculation using group increment values, which should be a more accurate calculation. And with this, just to help us out, what I'm going to do first is draw in all of the hydrogen. Because we do care about connectivity when we're thinking about the group increment values. Okay, so let's start with our reactants, and we'll actually be able to use some of the same values for the product as well. So we have in the alkene that we start with, these two carbons are identical, right? And I'm going to just label those as type A. All right, so type A, we have two of those. And how do we classify these? Well, these are double bonded carbons. So we would say CD, and that CD accounts for the double bond. All right, so what else is present? Well, in addition to the double bond, we have two hydrogen. So H2. All right, now, if we come over to our diene, well, look, here and here, we have the same thing, a carbon double bonded with two hydrogen. So these are also considered type A. So let's actually change this to 4. Okay, now let's look at our second type. These two, and they're identical. So we're going to label this as B. All right, how do we classify these? These are also double bonded carbons, CD. There's two of those. All right, so let's just kind of hone in on one and see what's going on. So this one on the top, the CD, the carbon double bond, is accounted for. But what else is attached? We have a hydrogen, and we also have a double bonded carbon, a CD. Okay, so let's go ahead and find the values for these. All right, so I'll pull up our group increment table for just a moment here. So what we're looking for is carbon double bonded to H2. We have that right here, 6.26. So I'm going to do 4, 6.26 kcals per mole. Right, then we're looking for a carbon double bonded to an H and a carbon double. So let's look down here. Here's CD bonded to a CD and an H. 6.78. Okay, so we can go ahead and add these up to get the heat of formation total for the reactants. I get 38.6 kcals per mole. So now let's jump over to our product and do the same thing. Let's go ahead and deal with our double bond first. These two, which are identical, we'll call that type C. Okay, and that is a carbon double. So there's two of those, so CD. And what is that bonded to? So obviously the double bond, but then it's bonded to a hydrogen and a carbon. Okay, now let's move on to the allylic carbons. Here and here. That's going to be type D. And there's two of those. All right, now that's not a double bonded carbon, that's a regular carbon, so we'll just say C. But what's it bonded to? It's bonded to a carbon double, a carbon, and two hydrogen. Right, and then finally, we have our last type, which we'll call E. And there's two of those. All right, what do we have here? Just regular carbon. If you look at one of these, it's bonded to two regular carbons and two hydrogen. Let's say C2, H2. All right, let's pull back up our chart. Okay, let's find type C. We have carbon double bonded to H and C. Right here, 8.59. So I'll do 2, 8.59, and all these are kcals per mole. All right, let's find D. It's just a regular carbon bonded to a carbon double, C and H2. All right, we have to go down our list a bit. Here's the carbons bonded to carbon doubles, and C, H2, so that is negative 4.76. There's two of those. All right, and then finally type E is just a regular carbon bonded to C2H2. Right here, that's negative 4.93. All right, let's add these up. With that, I get negative 2.2. So if we compare, our product has a negative heat of formation. Our reactants have a positive heat of formation, so the product is more stable. Now, we can calculate the delta H for the reaction by taking the heat of formation of the products minus the reactants. So this is going to be negative 2.2 minus 38.6. Right, if you do the math, you get negative 40.8. So again, this is telling us an exothermic reaction.